Yeah, welcome. So the topic we'll be discussing in this lecture is software performance issues. So we are discussing about multi-core computers. In the last lecture we have discussed about hardware performance issues, and in this lecture we'll be concentrating about software performance issues. So basically we'll be discussing here like what are the software issues that were faced in a multi-core environment, because generally softwares are not tuned towards multi-core environment, rather they are tuned for single core environment. Okay, so in a multi-core environment the performance benefits can be realized only by effectively exploiting the parallel resources. What are the parallel resources? The parallel resources are nothing but the multi-core. Multi-cores are the parallel resources. Okay, because in one chip you have more than one core. So these parallel resources should be effectively exploited. That means they should be best utilized. Then only their performance benefits can be realized. Otherwise, if the software that you are running on a multi-core computer is unable to exploit the performance benefits of the multi-core environment, then it means that we are not fully utilizing the multi-core facility. Okay, and another restriction is, say for example, in a particular piece of program, say maybe some part of the code, there may be a possibility that this code can be executed parallelly. Now if you have two cores, these codes you can divide and you can give it to each one of the cores. One core will do one half and another core will do another half. Okay, so this is applicable only to a part of a program. This is a single program, but the rest of the part of the program, it will be something like that you cannot execute this code parallelly. You have to execute it serially. So this is a restriction which is imposed by the software, because this program is designed in such a way that only certain part, say 80% of the code, can be executed parallelly, but the remaining 20% at any cost it should be executed serially. Then now even if you have a multi-core environment, then also only this 80% can be executed on two cores simultaneously. This remaining 20% should be executed only on one core, because the program is designed in such a way that they should be executed sequentially. Okay, yeah, but here there is a issue. What is the issue? Even if there is only 10% of the code, assume that in a piece of program 10% of the code should be executed serially. Remaining 90% of the code you can execute parallelly. Okay, and assume that the computer has 8 cores, that is there are 8 processors in a single system. Then also the performance gain will be only 4.7 times. Okay, which is actually less, because 90% of the code you are able to execute parallelly. So the performance improvement is not 9 times, it is only 4.7 times. That means even if there is a small amount of code that is to be executed in a serial fashion, that is going to affect the performance. That is what it says. See here, only 10% of the code are to be executed serially. Remaining 90% can be executed parallelly, but still the performance gain is only 4.7 times. Okay, so the point is, it is not only having the hardware, that is, it is not only having a multi-core hardware, that alone it is not sufficient. If the software, or if the softwares were unable to get best out of the multi-core environment, then even if you have the multi-core environment, you are not going to get benefited to that extent. Okay, so the software should be able to exploit the maximum utilization of the multi-core environment. Okay, further, in some cases, if in the software there is some part of the code which has to be executed serially, then that is also going to adversely affect the performance of the multi-core environment. Because even if there is a 10% of the code that is to be executed serially, that is going to affect the performance by 4.7 times. But there are certain applications which can effectively exploit the multi-core processors. So we'll be discussing some of those applications also. Okay, so the performance gain uh, can be can be measured by Amdahl's law. So sometimes back, I think in operating system we have discussed Amdahl's law. So Amdahl's law is given like this: time to execute a program on a single processor divided by time to execute program on n parallel processor. You take a typical application, okay? You take a typical application, say A1. To run this application A1 in one processor, how much time it takes? And to run the same application in n processors, that is n parallel processors are there, and this job is distributed and given to them, then it takes how much time? So that is what is called as Amdahl's law, and it can be represented like this: Amdahl's law is equal to 1 by 1 minus f plus f by n. What is f? F is the fraction of code that can be executed parallelly. So here f represents the fraction of code that can be executed parallelly, and 1 minus f represents the fraction of code that should be executed serially. Okay, f is the fraction of the code that can be executed parallelly, and 1 minus f is the fraction of code that should be executed serially. And n represents the number of cores. How many cores the computer has, that is called as n. Okay, so n is number of cores, right? Okay. So based on Amdahl's law, so this graph is plotted. Say for example, so this line, what it says in the sense, assume there is 0% of the code which should be executed serially. There is no code is to be executed serially. Okay, so sequential or serial. Okay, there is no code which is to be executed sequentially. In that case, if you have 8 cores, then the performance improvement will be 8 times. Okay, with 8 cores the performance improvement will be how much times? It will be 8 times. Okay, but see the next case. Even if there is a 2% of the code that should be executed serially, then the performance improvement is decreasing. Then the performance improvement will be only 7 times. Okay, if there is 5% of the code that is to be executed sequentially, remaining 95% of the code can be executed parallelly. Now the performance, the speed up is only 6 times. Okay, if there is 10% of the code that is to be executed sequentially, then the performance gain will be something around 4.7. Okay, so that's what we have discussed here. Here it says that when there is 10% of the code is to be executed in sequential or serial fashion, then the performance gain is only 4.7 times. Okay, it's not going to be 8 times. The maximum performance gain possible is 8 times, but here it is only 4.7 times, right? So this is also, so the amount of code that is to be executed serially, that is also going to adversely affect the performance of multi-core computers, right? So this graph is an ideal graph. This is an ideal situation. This graph is plotted. That is, it is only a theoretical representation. If this percentage of serial code is there, then this is the maximum performance gain you will get. Okay, but actually the performance gain will be less than this, because in reality we have some overheads. Okay, so this graph, it represents the theoretical speed up, but this graph represents the speed up with overheads. So in reality there will be some overheads. Okay, so when you with overheads, when you consider, it is still coming down. When the, what do you call, when there are 5% of the code is to be executed serially, then the performance gain is slightly greater than uh, 2 times. That's it. But actually here if you see, performance gain is 6 times, but when overhead is added, it becomes only 2 times. Okay, when there are 10% of the code is to be executed serially, then the performance gain is less than 2 times. It is only 1.9 or 8 times, but previously it is 4.7 times. Okay, when there is 15% of the code is to be executed sequentially, then the performance gain is almost 1.77 times. Okay, and when there is 20% of the code is to be executed sequentially, then the performance gain is hardly 1.6 times. Okay, so this is the real graph, this is in the real scenario, this is an ideal case, right? So again you can see the performance gain we are experiencing is very less. So even with 5% of serial code, remaining 95% can be executed parallelly. But here also the performance gain is it's hardly 2%. Okay, two times the performance gain when you are using 8 processors. Okay, actually it should be close to 8 if there is no overhead, but it is only, the performance gain is only twice or 2 times the normal performance. Okay, right. So next we will be discussing some softwares which can exploit the best utilization of multi-core processors. So there are certain softwares which can take uh, better utilization out of multi-core processors. These are mainly database applications, because in database applications you may have to do certain things and seek parallelly. So in such cases, multi-core processors, two cores will be used effectively, right? Server handling independent transaction. So if there is a server, and in that server, or you have multiple servers, each server to handle one transaction. Okay, then each server can be given to one core. So if you have 8 cores, and if there are 8 requests, then each what do you call, or if you have 8 servers and there are 8 cores, then whatever the job submitted by one first server, it can be given to first core. Second server, whatever the job submitted, it can be taken care by second core, and so on and so forth. And when there is a multi-threaded applications, in multi-threaded environment also, the multi if the I mean if the software needs if the software or multi-threaded software, there are more than one thread simultaneously executing, then each thread can be given to each core. So multi-threaded applications can also exploit the better utility of multi-core processors. Okay, and then multi-process applications. So multi-thread means, thread is a lightweight process, right? One process, there are different execution path, that is called as thread. And multi-process means there are applications in which there will be multiple processes created simultaneously, and all these processes should be executing simultaneously. In such environment also, multi-core processors uh, the will be utilized to the maximum extent. And then Java applications. See, Java is basically, it's a multi-threaded language, so it supports multi-threading. Okay, and also when you run the Java program, at the background the memory management software will be keep running. Okay, which is something like a garbage collector. So whenever you are running Java, more than one thread is executing. So in that case, the background threads can be handled by a different core, and the foreground thread can be handled by a different core, right? So Java applications can also exploit the best performance out of multi-core processors, right? Okay, and then there are certain applications in which multiple instances are to be executed simultaneously. That means you may want to execute the same program again and again. Okay, so in that case also multi-core processors will be better utilized. Okay, because each instance can be handled by a different core, right? So that's it about software performance issues with multi-core processors. Next, multi-core computers or multi-core processors. Next, we will be discussing about multi-core organization. So the way in which the multi-core processors are organized can be categorized into 3 categories. These are based on number of processors on a chip. Okay, one is based on number of processors on a chip, we can categorize, and then number of levels of cache on the chip. How many levels of cache are there? Based on that also we can categorize, and then based on the amount of shared cache. Okay, in a processor, in a chip, how much amount of cache is shared and how much amount of cache is not shared. Not shared means some cache may be dedicated for a particular core. Okay, so how much that? Based on that, the multi-core processors are categorized. So based on number of processors, based on the levels of cache on each, on the chip, levels of cache, how many levels of cache, whether it is L1 and L2 or L1, L2, L3 or any other different level. Okay, out of these caches, how much cache was shared and how much cache was not shared. Okay, so these are some of the example processors which uses multi-cores: ARM 11, MP core, AMD Optron, Intel Core Duo, Intel Core i7. All these are multi-core processors. Okay. Now let us see the different organization. So this diagram actually shows the various organization. The first one is a dedicated L1 cache. Here you can see in a single chip there are two cores. There is a core 1, not only two cores, there can be any number of cores. Core 1 up to core n. Okay, there are n cores. Each core, each core is having its own L1 cache. Each core is having its own L1 cache. So in L1 cache there is a separate cache for instruction part and there is a separate cache for data part. Okay, so there are what you call, in the chip there can be any number of cores and each core will have its own dedicated L1 cache, and this L1 cache there will be a separate data cache and instruction cache. Okay, right, and there is L2 cache, but this L2 cache is kept outside the chip, it is not inside the chip. Okay, and then there is memory and IO. So this is called as dedicated L1 cache. Okay, so here next you can see this organization is dedicated L2 cache. This is dedicated L2 cache. So here inside the chip there are many cores. There are many cores. Each core have its own L1 cache. Okay. Again, this L1 cache is divided into instruction cache and data cache. But each core also has its own L2 cache. This core 1 has its own L2 cache. Core 2 will have its own L2 cache, so on and so forth. This core n also have its own L2 cache. That is, every core have its own L2 cache, and all these are in the same chip. Okay, this is the chip, right, and the main memory is outside the processor, right. So this is second configuration. The third one is shared L2 cache. Shared L2 cache. Here inside the chip there are multiple cores. Each core has its own L1 cache. Again there is L1 instruction cache and L1 data cache. But the L2 cache, you can see the L2 cache is shared among all the cores. L1 cache is different. Each core has its own L1 cache, but the L2 cache is shared among all cores. L2 cache is still inside the chip, but it is shared among all the cores. Okay. And the fourth category is shared L3 cache. Here if you see, there are multiple cores inside the chip. Each core has its own L1 cache. L1 cache contains instruction and data cache, and each core has its own L2 cache also. But L3 cache is shared. There is a L3 cache which is also inside the chip, but that is shared. Okay. So these are the different way of multi-core organization alternatives we have. Okay. So if you have so ARM 11 MP core, it follows this dedicated L1 cache. Okay. Similarly, the next one, it follows dedicated L2 cache. Okay, and this one follows shared L2 cache, and this follows shared L3 cache. Okay, these are the different organizations. Okay. So actually if you see, out of these four, this one and this one will perform better, because here we have shared L2 cache and here we have shared L3 cache. So this particular organization will perform better. Why is it so? That we will see. So when the L2 cache is shared, we have several advantages. What are they? First, it reduces the overall miss rate. It reduces the overall miss rate. Okay, because you have private L1 cache and shared L2 cache. So if something is not in L1 cache, then it may be available in L2 cache. So the probability of cache miss is less. Okay, and data shared on multiple cores are not replicated. Okay, so say for example, if there is some content is to be shared between two cores, if there is a particular variable that is to be shared between two cores or all the cores, then better that content will be in L2 cache. Okay, so that because L2 cache is shared among all the processors, so everybody can access it. Okay, if you keep it this in L1 cache, then multiple copies should be kept, so that can be avoided by using L2 cache. So data shared and you need not replicate the same data on multiple cores. Okay, and with proper frame replacement algorithms, the amount of shared cache dedicated to each core is dynamic. Thread with less locality can have more cache, which means that, see, even though there is a shared L1 cache, but this L1 cache again will be divided. Like core 1 should get this much, core 2 should get this much, like that it will be divided. But there is no standard definition of division for that. This category of dividing, it happens dynamically. It happens dynamically. So whichever the core whose locality is less, locality means what? Locality of reference. So locality of reference means what? Uh, so we discussed locality of reference. Which data is to be cached in the sense, the data which is recently, there are two types of locality of reference. If you remember, we have discussed temporal locality and spatial locality. Temporal locality means the data which is requested recently, it is highly expected that will be again required by the processor. Spatial locality means the data of a particular location, memory location X, if it is requested at time t, then it is highly likely that x plus 1, that location also will be required after some times. Okay, right? So generally this is the rule. Generally this is the rule, locality of reference. Based on that, the I mean, what is the data which will be accessed next can be calculated, right? So generally that is the scenario, but at certain cases the locality of reference may not work. Sometimes the processor may randomly ask some data. Okay, in such cases, if the locality of reference is low for a particular process, okay, or for a particular core, a core is running a process, right? So in that case, for that core you allocate more L2 cache. For remaining cache, for remaining cores you allocate less L2 cache, because they are having higher locality of reference. So they may need to store less amount of data in the cache. They need not store more amount of data. But if the locality of reference is low, then they have to store more amount of data. Okay, so that's what it says. Threads with less locality of reference can have more cache. Okay, and with shared L2 cache, inter-process communication is also possible. Two processes can communicate through the shared cache. They can pass messages among each other. Okay, and cache coherence is limited to only L1 because L2 is shared. So cache coherence means what? Cache should be consistent. If CPU, if core 1 is modifying this cache, then it should intimate to everybody, and it should make sure that everybody is updating or making their content invalid, all those things. So that cache coherence, now the operating system need to worry about cache coherence for only L1. L2 there is no question of cache coherence because it is shared with all the cores. Okay, so these are some of the advantages of L2, I mean shared L2 cache. Okay, further we can also go for shared L3 cache, which will also improve the performance. So that is what's shown in this diagram. Here there is a dedicated L1 and L2 cache for each course, but L3 cache is shared. Okay. Right. Okay, now let us discuss about some of the architectures briefly. So individual core architecture. Okay, so for example, if you see Intel Core Duo, it is one type of processor. It uses superscalar cores. Superscalar means uh, it's a Intel core. There are multiple cores, but each core contains superscalar units. That is, there are multiple functional units. Like it may have more than one ALU, it may have two ALUs or three ALUs. Okay. Whereas Intel Core i7, it uses SMT, symmetric multithreading, right? So with it uses four SMT cores. It uses four SMT cores in such a way that each of these SMT cores can support four threads simultaneously. Okay, so actually it gives an appearance to the user as if there is 16 cores. Okay, so previously we have discussed about SMT, right? So 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 there are four cores simultaneously, and each core supports four threads. So it means that it can execute different thread. It can execute 16 different threads during one clock cycle. During a particular clock cycle, it can execute 16 different threads. Are you getting? Because there are 4 cores, 4 SMT cores, and each core can support 4 threads. So if you have 16 threads and there are certain code in all these 16 code threads to execute parallelly, then in one clock cycle all 16 threads can be executed. Okay. So if you take x86 multi-core organization for core duo, it was introduced in the year 2006. It has two x86 superscalar processor and it has shared L2 cache. There is a separate L1 cache, but there is a shared L2 cache. The dedicated L1 cache per core, there is a dedicated L1 cache per core which contains 32 KB instruction cache and 32 KB data cache. Okay, this is one particular type of Intel processor which uses shared L2 cache, and it has a L1 cache per core where 32 KB goes for instruction cache and 32 KB goes for data cache. It also uses this particular x86 multi-core core duo processor. It also uses thermal control unit in each core, okay, which is used to reduce the heat dissipation, and thereby it increases the performance. Okay, and also this particular processor core 2 core duo, it also uses something called as APIC, advanced programmable interrupt controller. Okay, advanced programmable interrupt controller, which is used to create interrupt between two cores. Okay, if the processor which are running in one core want to interrupt the process in another core, that is done by a unit called APIC, advanced programmable interrupt controller, which is used to generate inter-processes interrupts between cores. It routes interrupts to appropriate core. Okay, for that it uses a timer so that OS can interrupt. It also includes a power management logic which monitors the thermal conditions and CPU activity, and accordingly it adjusts the voltage and power consumption. Okay, and it has a 2 MB shared L2 cache. Right, previously we discussed, only we know that there is a shared L2 cache. The capacity is 2 MB. Okay, whereas L1 cache capacity is, it has two sets of 32 KB instruction cache and 32 KB data cache. Okay, so this shared L2 cache, it supports MESI protocol. Okay, it supports MESI protocol for L1 cache, because L2 cache there is no cache coherence. Cache coherence required for L1 cache only, not for L2. Okay, so MESI, I guess you remember, modified, exclusive, shared, and invalid. Okay, right. So this is the typical configuration of core 2 duo. You can see there are two cores. This is core 1 and this is core 2. So each core is having L1 cache 32 KB. What do you call it? There are 32 KB instruction cache and 32 KB data cache. So this is for core 1 and this is for core 2. Okay, and they have thermal control unit, APIC, power management logic, and there is a shared L2 cache of size 2 MB, and there is bus interface which connects the CPU bus with the system bus. Okay, right. APIC stands for Advanced Programmable Interrupt Controller. So this is the organization of Intel Core Duo. Similarly, if you see Core i7, it is released in the year 2008. It has 4 SMT processors. It has dedicated L2 and shared L3 cache. So it means it has dedicated L1 and L2 cache, and dedicated L1 and L2 cache, and L3 cache is shared. It performs prefetch for caches. Okay. It has on-chip DDR3 memory controller. Okay. It uses the DDR3 memory controller, 3 8-byte channels. Okay, and no, it does not use any front side bus. So this is the configuration for Intel Core it is i7, right? Intel Core i7. Okay, so here you can see there are four cores: core 1, core 0, core 1, core 2, and core 3. Each core contains 32 KB data cache and 32 KB instruction cache. Okay, and each core has a dedicated 256 KB L2 cache, and there is a 8 MB L3 cache. Okay, L3 cache size is 8 MB. Okay, right, and there are memory controllers for DDR3, which means through this it connects with the main memory. Through this it connects with the main memory, and this is a quick interconnect path that is to connect with what do you call high speed communication link with other processor chips. Okay, and for data transfer with other processors at a faster rate. Okay, so this is the configuration of core i7. Right, that's it, we'll stop here. Okay, so that's it about this particular topic. So here we have discussed two topics. One is software performance issues and the other one is multi-core organization. So with this topic gets over. Okay, so fine, we'll stop here. Thank you.